Welcome. In this session, we'll explore the problem contains duplicate 3. It's a fascinating challenge that combines concepts of arrays, hashing, and efficient data structures. By the end, you'll have a clear understanding of the problem and the approaches to solve it. Let's get started. In this problem, we are given an array of integers called nums and two integers k and t. The task is to determine whether there exist two distinct indices, I and j, in the array such that two conditions are satisfied. First, the absolute difference between the elements at these indices, nums, I, and nums, j, must be at most t. Second, the absolute difference between the indices themselves, I and j, must be at most k. If both conditions are met for any pair of indices, we return true, otherwise, we return false. The input consists of the array nums, which can have up to 20,000 elements, and the integers k and t with given constraints. The output is a Boolean value, true if such a pair exists, and false otherwise. For instance, consider the first example. Here, nums is 1, 2, 3, 1, k is 3, and t is 0. The output is true. This is because the pair of values nums, 0, equals 1 and nums, 3, equals 1 satisfies both conditions. The absolute difference between these values is 1, 1 equals 0, which is less than or equal to t. Additionally, the absolute difference between their indices is 0, 3 equals 3, which is less than or equal to k. Since this pair meets all the requirements, the output is true. Now let's look at another example. In the second example, nums is 1, 0, 1, 1, k is 1, and t is 2. The output is again true. Here, the pair nums, 2, equals 1 and nums, 3, equals 1 satisfies the conditions. The absolute difference between the values is 1, 1 equals 0, which is less than or equal to t. The absolute difference between their indices is 2, 3 equals 1, which is less than or equal to k. Therefore, this pair meets the criteria, and the result is true. On the other hand, consider the third example. In the third example, nums is 1, 5, 9, 1, 5, 9, k is 2, and t is 3. Here, the output is false because there is no pair of indices that satisfies both conditions at the same time. The constraints for this problem highlight key considerations. The array nums can have up to 20,000 elements, and the values of k and t can be very large. Special cases include situations like when nums has fewer than 2 elements, where the output is always false because there are no pairs to compare. If k is 0, the indices cannot satisfy the condition of being distinct and close enough. Similarly, when t is 0, the problem simplifies to finding exact matches between elements. Lastly, efficient handling of large inputs and values is crucial to meet the problem's requirements. To tackle the problem, the most intuitive approach is the brute force method. Here, we check all pairs of indices, I, j, in the array. For each pair, we verify two conditions. First, the absolute difference between the numbers at those indices, nums, I, nums, j, must be less than or equal to t. Second, the indices themselves must be close enough, meaning ij should be less than or equal to k. While this method is straightforward to implement, it involves examining every possible pair, leading to a time complexity of n squared. This quadratic growth makes the approach impractical for large arrays because the number of comparisons quickly becomes overwhelming. However, it does have the advantage of requiring minimal space, making its space complexity 1. Overall, while simple, this approach is inefficient for handling large datasets. An alternative strategy involves using a sliding window combined with a sorting mechanism. Here, instead of comparing all pairs, we focus on a smaller subset of elements within a sliding window of size k. The idea is to maintain the elements in this window in a sorted data structure. For each new element in the array, we use binary search to pinpoint the range of values within the current window that satisfy the condition nums, I, t equals nums, j equals nums, I, plus t. If a valid number is found, the condition is met. As the window moves forward, the oldest element is removed to ensure the window size does not exceed k. This method is more efficient than brute force, reducing the time complexity to n*log k due to the logarithmic cost of maintaining the sorted structure. However, it introduces additional implementation complexity and requires extra space proportional to the window size, OK. Despite the trade-offs, this method offers a significant improvement in efficiency. Another efficient strategy is the bucket-based approach, which leverages the problem constraints in a clever way. The insight here is that if two numbers differ by at most t, they must either fall into the same bucket or adjacent buckets when the number line is divided into buckets of size t plus 1. To implement this, we assign each number to a bucket based on its value, where the bucket index is calculated as nums // t plus 1. For each new number, we first check its own bucket and the two adjacent buckets for any number that satisfies the condition. To ensure the sliding window constraint is respected, we maintain only the buckets corresponding to the most recent k elements by removing buckets that fall out of range. This approach eliminates the need for sorting and achieves linear time complexity, O(n). It also requires minimal additional space, O(k), but it's important to handle edge cases, such as negative numbers, carefully. This method strikes an excellent balance between efficiency and simplicity. Among the strategies discussed, the bucket-based approach stands out as the most efficient and scalable solution. Its linear time complexity makes it ideal for handling large inputs, and it avoids the overhead of maintaining a sorted structure. This method is particularly appealing because it leverages the constraints of the problem effectively. The sliding window ensures that indices I and j remain within a distance of k, while the bucket size of t plus 1 guarantees that only relevant numbers are compared. The key insight or aha moment here is realizing that comparisons can be restricted to numbers within the same or adjacent buckets. When comparing all approaches, the brute force method is too slow for large inputs, the sliding window with sorting is efficient but more complex to implement, and the bucket-based method combines optimal runtime with simplicity, making it the most practical choice for this problem. In conclusion, the bucket-based approach is the optimal choice for solving this problem due to its efficiency, scalability, and ease of implementation. By taking advantage of the sliding window and bucket constraints, it ensures that comparisons are limited to relevant numbers, achieving constant time operations for each comparison. This balance of runtime efficiency and straightforward implementation makes it well suited for handling large datasets. Overall, this approach effectively addresses the problem's constraints while minimizing computational overhead, making it the best solution. The goal of this problem is to determine if there exist two indices, I and j, in the array nums that satisfy two specific conditions. First, the absolute difference between the elements at these indices, nums I, nums j, must be at most t. This means the values of the elements should be close enough, within the given threshold t. Second, the absolute difference between the indices themselves, I, j, must be at most k. This ensures that the two elements we are comparing are not too far apart in the array. The challenge is to check for such a pair of indices efficiently, especially given the potential size of the array and the constraints of the problem. One way to solve this problem is using a brute force approach. Here's how it works. First, we iterate over all possible pairs of indices, I, j, in the array. This is done using two nested loops. The outer loop moves through each index I from the start of the array, and the inner loop examines every subsequent index j after I. For each pair, I, j, we check if both required conditions are satisfied, whether the absolute difference between the values at these indices is less than or equal to t, and whether the indices themselves are close enough, within a distance of k. If we find any pair that meets these criteria, we return true. If no such pair is found after examining all possibilities, we return false. While this approach is straightforward, it becomes inefficient for large arrays because it requires examining every possible pair, leading to a time complexity of O(n squared). To improve efficiency, we can use an optimized approach that combines a sliding window with a balanced data structure like a sorted set. Here's how this works. First, we maintain a sliding window of size k, which ensures we only consider elements within the required index range. The elements in this window are stored in a sorted set, which allows us to perform efficient range queries to check the value difference condition. As we iterate through the array, for each element, we check if there's any number in the sorted set that satisfies the condition nums I, nums j equals t. If such an element exists, we return true. After the check, we update the sliding window by adding the current element to the sorted set. To keep the window size at most k, we remove the oldest element from the set if the window exceeds this size. If we complete the iteration without finding a valid pair, we return false. This approach significantly reduces the time complexity by leveraging the efficient operations provided by the balanced data structure. When comparing the brute force and optimized approaches, several key insights emerge. First, the brute force method is limited by its n² time complexity, which makes it impractical for large arrays. In contrast, the optimized approach, using a sliding window and a sorted set, reduces the complexity by focusing only on elements within a fixed index range of size k. The sorted set is particularly valuable because it allows us to efficiently check the condition nums I, nums j equals t through its range query capability. Additionally, by limiting the sliding window to k elements, we avoid unnecessary comparisons with elements outside the range of interest. This optimization not only improves performance but also aligns the algorithm more closely with the problem constraints. The optimized solution relies heavily on two key data structures. The first is the sorted set, or an equivalent balanced binary search tree. This structure allows us to maintain the sliding window of elements while supporting efficient insertion, deletion, and range queries, all in logarithmic time. Examples include treeset in Java or the sorted list from Python's sorted containers library. The second is the sliding window itself, which ensures that we only consider indices within a range of size k. By combining these two components, the algorithm efficiently narrows the search space and checks for valid pairs without unnecessary computations. Let's analyze the complexities of the two approaches. The brute force method has a time complexity of n² because it involves two nested loops to check all possible pairs. The optimized approach, on the other hand, has a time complexity of n log k. Here, n is the length of the array, and k is the size of the sliding window. The logarithmic factor comes from the operations on the sorted set, such as insertion, deletion, and range queries. For space complexity, the optimized approach uses k space to store the elements in the sorted set, as the size of the sliding window is limited to k. This makes the optimized solution far more scalable for large arrays. Finally, it's important to consider edge cases. For very small arrays, specifically those with fewer than 2 elements, the result is always false because no pairs can exist. When k is larger than the array size, the entire array effectively becomes the sliding window, so all indices are considered for valid pairs. If t is very large, almost all differences between elements will satisfy the condition nums I, nums j equals t. Additionally, the algorithm must handle duplicate values correctly. Even if 2 elements are equal, the index condition j equals k must still be satisfied for the pair to be valid. These scenarios highlight the importance of carefully implementing the solution to ensure correctness in all cases. This solution efficiently solves the problem using the sliding window and a balanced binary search tree provided by the sorted list from the sorted containers library. The algorithm ensures that for each index I, it considers a sliding window of at most k elements to maintain the constraint j equals k. To check the difference constraint in nums I, nums j equals t, it uses binary search to find potential candidates within the range nums I, t, nums I, plus t. One edge case handling asterisk. The function starts by ensuring that if t less than 0 or k equals 0, it immediately returns false, as these cases violate constraints. 2. Sliding window maintenance asterisk. The sorted underscore list tracks the numbers in the current sliding window. If the window size exceeds k, the oldest element is removed to maintain the size constraint. 3. Binary search for range check asterisk. The bisect underscore left method finds the lowest index where nums I, t could be inserted. This ensures that the search focuses on elements that could potentially satisfy the condition nums I, nums j equals t. For a validation of range asterisk, once the candidate position is found, the algorithm checks if the number at that position is within the acceptable range of nums I. If a valid number is found, the function returns true. 5. Adding current element asterisk. If no valid number is found, the current number nums I is added to the sorted underscore list to include it in the sliding window for future checks. The algorithm runs an n asterisk log k time, where n is the length of the input list and k is the sliding window size. This is due to the log k complexity of operations like insertion and removal in the sorted list. It is efficient for large inputs and adheres to the problem's constraints. Here, we start by importing the necessary utilities and defining our solution class with the method contains nearby almost duplicate. This method takes an array of integers, nums, and two parameters, k and t. The first thing we check is whether t is negative or k is less than or equal to 0, as these conditions immediately make the problem invalid, so we return false. Next, we initialize a tree set, which is a data structure that helps us maintain sorted order and allows for efficient range queries. Now, we iterate through the array using a for loop. For each number, we check if there is a value in the tree set that falls within the range of nums I, t, nums I, plus t. To achieve this, we use the floor method to find the largest number less than or equal to nums I, plus t, and the ceiling method to find the smallest number greater than or equal to nums I, t. If either of these values satisfies the condition, we return true. Otherwise, we add the current number to the tree set. Finally, to enforce the sliding window constraint, we ensure the tree set only keeps at most k elements by removing the element that is out of range, which is nums I k. After iterating through all the elements in the array, if no valid pair is found, we reach the end of the method and return false. This ensures that the function only returns true if it detects a pair of indices that satisfy the given conditions. With this implementation, the tree set helps us efficiently maintain the sliding window and check for nearby duplicates within the specified range. To solve this problem, we start with the given example where nums is 1, 2, 3, 1, k is 3, and t is 0. The solution uses a sliding window technique with a sorted list to efficiently keep track of the elements within the range of k indices. Initially, the sorted list is empty. For the first element, nums 0 equals 1. Since the sliding window condition I greater than k is false at this point, there's no need to remove any elements from the sorted list. We calculate nums I, t, which is 1 to 0, giving 1. Using this value, we determine the position in the sorted list where the current number could be inserted, which in this case is position 0 because the list is empty. There are no nearby duplicates since the sorted list has no elements yet. We then add nums 0 to the sorted list, resulting in sorted_list equals 1. Next, for nums 1, which is 2, the sliding window condition again does not require any removal. We compute nums I, t, which is 2 to 0, giving 2, and find that the position to insert it is 1. Checking for nearby duplicates, we find no element within the allowed difference of t. We add nums 1 to the sorted list, so it becomes sorted_list equals 1, 2. Now, for nums 2, which is 3, the calculation nums I, t gives 3 to 0, which equals 3. The position for insertion is determined to be 2. Again, there are no nearby duplicates since all differences exceed the threshold t. We add nums 2 to the sorted list, updating it to sorted_list equals 1, 2, 3. Finally, for the fourth iteration with nums 3 equal to 1, the calculation nums I, t results in 1 to 0, giving 1. This time, the position for insertion is 0. When we check for nearby duplicates, we find that the absolute difference between sorted_list 0 and nums 3 is abs 1 to 1, which equals 0. This is less than or equal to t, meaning we've found a match. At this point, the function returns true, confirming that the condition is satisfied for this example. In the second example, nums is 1, 5, 9, 1, k is 2, and t is 3. We start by initializing an empty sorted list. For the first iteration, nums 0 equals 1. The sliding window condition does not require any removal, so we compute nums I, t, which is 1 to 3, resulting in -2. The position for insertion is determined to be 0. Since the sorted list is empty, there are no nearby duplicates. We add nums 0 to the sorted list, resulting in sorted_list equals 1. Next, for nums 1, which is 5, the calculation nums I, t gives 5 to 3, which equals 2. The position for insertion is 1. Checking for nearby duplicates, there are no elements within the allowed range of t. We add nums 1 to the sorted list, updating it to sorted_list equals 1, 5. For nums 2, which is 9, the calculation nums I, t results in 9 to 3, giving 6. The position for insertion is determined to be 2. Checking for nearby duplicates, we find that no elements in the sorted list meet the condition. We add nums 2 to the sorted list, which becomes sorted_list equals 1, 5, 9. Finally, for nums 3, which is 1, the sliding window condition now applies because I greater than k, so we remove nums 0, which is 1, from the sorted list. After this removal, we calculate nums I, t, which is 1 to 3, resulting in -2. The position for insertion is 0. Checking for nearby duplicates, there are no matches within the allowed difference of t. We add nums 3 to the sorted list, which remains sorted_list equals 1, 5, 9. Since no match was found throughout all iterations, the function returns false for this example. In the final example, nums is 1, 2, k is 2, and t is 2. As always, we start with an empty sorted list. For the first iteration, nums 0 equals 1. The sliding window condition does not require any removal, so we compute nums I, t, which is 1 to 2, resulting in -1. The position for insertion is determined to be 0. Since the sorted list has no elements, there are no nearby duplicates. We add nums 0 to the sorted list, resulting in sorted_list equals 1. For nums 1, which is 2, the calculation nums I, t gives 2 to 2, which equals 0. The position for insertion is 0. Checking for nearby duplicates, we find that the absolute difference between sorted_list 0 and nums 1 is abs 1 to 2, which equals 1. This is less than or equal to t, indicating a match. The function returns true, confirming that the condition is satisfied for this example. Here, we're analyzing the time complexity of the solution. The algorithm relies on a sliding window approach combined with a sorted list from the sorted containers library, which is essentially a self-balancing binary search tree. The time complexity is influenced by 3 main operations. First, maintaining the sliding window. When the window size exceeds k, an element is removed from the sorted list, which takes O log k time because the list must maintain its sorted order. Second, performing a binary search to check if a value within the required range exists. This is accomplished using the bisect_left operation, which also operates in O log k, due to the sorted nature of the list. Lastly, adding the current number into the sorted list requires O log k, as it involves insertion into the balanced tree structure. Since the loop processes each of the n elements in the input array, and each iteration involves these 3 operations, the dominant cost per iteration is O log k, leading to a total time complexity of O n log k. Combining the costs explained earlier, we get the total time complexity of the algorithm as O n multiplied by O log k, which simplifies to O n log k. Now, let's move to the space complexity. The primary contributor to space usage is the sorted list, which stores up to k elements at any given time because the sliding window is limited to size k. Beyond that, the only additional space used is for variables necessary for the iteration and computations, which is constant and doesn't scale with input size, making it O(1). Therefore, the overall space complexity of the solution is determined by the sorted list, resulting in OK. Let's break the algorithm's performance into best, average, and worst-case scenarios. In the best case, if the input has invalid parameters such as t less than 0 or k equals 0, the function exits immediately without entering the loop. This results in a time and space complexity of just O(1). For the average case, when the input is randomized, the algorithm processes all n elements and performs O log k operations per iteration, leading to O n log k time complexity and O k space complexity. In the worst case, where the entire array must be processed and no early exit is possible, the time complexity remains O n log k, and the space complexity is still O k. Comparing this to a brute force approach, which checks all valid pairs I, j, and has a time complexity of O n squared, the optimized solution provides significant improvement. The space complexity of the brute force approach is O(1), but the time savings of the optimized approach, especially for large inputs where n and k are on the order of 10 to the power of 4, make it far more practical. To solidify our understanding, let's summarize the mathematical proof for the algorithm's big O complexity. First, each binary search and update operation on the sorted list has a cost of O log k, thanks to the balanced tree structure it employs, and this behavior holds regardless of the input values. Second, the loop runs exactly n times, as each element in the input array is processed once. Combining these, the total time complexity becomes n asterisk O log k, which simplifies to O n log k. Finally, the space complexity is straightforward. The sorted list contains at most k elements, so the space usage is bound by O k. By leveraging the efficiency of binary search and sliding window techniques, this algorithm significantly reduces computational overhead, making it well suited for practical applications, even with large constraints. One of the most common mistakes in this problem is misunderstanding the difference between the two constraints, k and t. Remember, k refers to the maximum allowable difference in indices, while t refers to the maximum difference in values. Confusing these can lead to faulty logic in your solution. Another issue is relying on a brute force approach without optimization. While iterating through all pairs might work for small input sizes, it quickly becomes infeasible for larger inputs due to its n squared time complexity. You'll want to explore more efficient strategies for cases where n is very large. Additionally, edge cases like an empty array, or when k and t are 0, can cause runtime errors if not explicitly handled. It's important to account for these scenarios in your code. Lastly, be cautious with floating point arithmetic when comparing value differences, as precision errors can arise. Stick to integer-based calculations for accurate results. And if you're using an optimized approach like a sliding window or balanced BST, make sure you properly manage the window. Failing to remove elements outside the range of k can lead to incorrect outputs. In an interview setting, clarity on constraints is essential. Interviewers often check if you truly understand the problem, so take the time to clarify details like what absolute difference means and how both k and t constraints are enforced efficiently. It's also important to discuss trade-offs between different approaches. For example, why might you choose a sliding window technique over a tree-based solution? Highlight the time and space complexity of your approach and explain why it suits the given input size. Another key aspect is edge case handling. Make it a habit to mention scenarios like empty arrays, single-element arrays, or extreme values of k and t when explaining your solution. This shows you're thinking comprehensively about the problem. Lastly, recognize this question as part of a larger pattern. It's a variation of sliding window problems and range-based queries. Interviewers might probe your knowledge of similar patterns, so being able to relate this problem to other techniques is a great way to demonstrate your problem-solving depth. This problem has strong connections to other challenges on LeetCode, and recognizing these can help you build intuition. For example, LeetCode 217, contains duplicate, is a simpler version of this problem that doesn't include constraints on k or t. It's a great starting point to understand the basic concept of detecting duplicates. The current problem, LeetCode 220, adds the complexity of k and t constraints, making it much harder. Another related problem is LeetCode 523, continuous subarray sum, which involves finding subarrays with specific constraints. This is another good example of applying sliding window techniques. Finally, LeetCode 480, sliding window median, is a range-based query problem that, instead of focusing on differences, involves calculating medians within a sliding window. These related problems share overlapping concepts like sliding windows, efficient range queries, and managing subsets of the input array, so understanding their similarities can strengthen your grasp of this problem and others like it. When choosing an approach, it's important to weigh the trade-offs between efficiency and complexity. The brute force solution, with its n squared time complexity, is straightforward but impractical for larger inputs. This method is only useful for very small datasets. A more efficient option is the sliding window approach combined with a hash set, which runs in n time. However, it's limited to enforcing the k constraint and doesn't directly handle t. For the most optimal solution, using a tree set or a balanced binary search tree is ideal. This approach achieves a time complexity of n log k, and can effectively enforce both k and t constraints. Tree set enables efficient range queries and ensures the sliding window is managed properly, though it requires additional space and can be harder to implement under time pressure. Alternatively, the bucket sort method provides an n solution by grouping numbers into ranges defined by t. While efficient, it's less intuitive and requires careful handling of edge cases to avoid errors. Each approach has its pros and cons, so choose based on the problem constraints and input size. Great job following along. To summarize, we tackled the contains duplicate 3 problem and reviewed both brute force and optimized approaches. Remember the importance of data structures and edge case analysis. Stay tuned for more tutorials, and don't forget to like and subscribe. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!